Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on current initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Peter Copeland. He's a professor of geology and thermochronology at University of Houston. I'm going to talk about radiometric dating and some other work he's doing. So, Peter, thank you for coming.
Thanks for inviting me.
If you would, tell me about a little bit about your background and how you got into the position of professorship, and then I want to ask you about your current work.
Well, I grew up in Kansas and got my bachelor's degree at the University of Kansas, where I first had no real interest in geology until I took a course in geology and found that the guys in the geology class seemed to be like the kind of guys I wanted to hang out with. Later on, I got a master's degree at New Mexico Tech, which was very good, and then I got a PhD in the State University of New York. From the time that I was a graduate student till pretty much now, I've been involved in various ways in which geochemistry can be used to help understand tectonic problems, how it is that big scale things happen on Earth, plates moving around, mountain belts being formed, and basins being formed sometimes. And geochemistry can often give insights into that. In particularly, the kind of geochemistry that I've been involved in is geochronology, figuring out the age of things, because obviously knowing when things happened is a key to telling the story. And even a sort of subdivision of geochronology is this thing called thermochronology, which is the ability to tell not just how old a rock is, but specifically tie that time to a particular temperature. Rocks can go through many different temperatures, from the surface temperatures we have here away down deep in the crust to hundreds of degrees Celsius. And when a rock is changing temperature, usually something interesting is happening to it. So we can, by applying various applications, we can understand a lot about the history of a rock by knowing when it was at various temperatures.
So what happens to rocks as they increase or decrease in temperature, inside the Earth? What kind of changes do they undergo?
Well, the Earth is hotter inside than it is outside. We've got a molten core down there and thousands of degrees down there. But in the uppermost part of the crust, we can say that the variation in temperature varies by approximately about 25 degrees Celsius for every kilometer you go down. It's not perfect. There's variations. Sometimes it's more or less than that. But in general, we can say that the further down you go, the hotter it is. And so by understanding when rocks change temperature, we can understand how it is they are moving relative to the surface of the Earth. And the reason that they do that movement relative to the surface of the Earth is either because of erosion. We're taking material off the top, and so the stuff down there gets closer to the top. or it can, and that erosion can just be the simple work of wind and water. The rain falls and grains of sand are moved from the mountains to the beaches. There's also a sort of tectonic erosion in which faulting and folding of rocks can change the thickness of the crust, which will then affect the temperature structure. So the position of rocks in the crust are complex interplay of erosion and tectonics, and the temperature is reflected there.
I have a quick question. There was this show on National Geographic called Cities of the Underworld, and they would go into Edinburgh and dig down, and they would see another city that was there hundreds of years ago and dig down again, etc. How do these, is that common that a city will fill up with dirt and earth and be covered, even if it's, dozens of feet high of cover? Like, how does that happen if so?
Well, you either have to have the city be abandoned by people who stopped maintaining it, or it has to happen all at once in one big thing. Vesuvius is a well-known example of a city that was covered up by a volcanic eruption. Other ones of these, some of the abandoned cities of the Anasazi Indians in Western North America, for example, they just seem to be abandoned and sort of fell apart. And eventually, they'll get covered up. There was an article
like in Rome. I saw they had an episode, which was a good one. You could dig down and go back in time 500 years. You could dig down further. Now it's 1,000 years. Why do things seem to get buried and covered over and covered over?
Well, some places are naturally sinking. Well, I think Rome might be an example. I'm not sure, but some places the earth is simply dropping because of if some places mountains are going up, other parts of the earth are not, and so some places are natural basins where sediment will accumulate. And New Orleans would be an example of some place that sits very near sea level or below sea level. And if you abandon New Orleans in a few thousand years, it would be filled up with all the silt that the river brings it. Now, Machu Picchu it's not going to happen to it. It's a city on the top of a mountain. So not every ancient city will be buried. Some will just be eroded and leave no trace.
Yeah, it just amazes me that how any city could get buried. It's weird, but it seems to happen pretty frequently.
Well, the processes of geologic processes will carry on whether we either maintain the city or not, and eventually they take it over.
Yeah, no, that's true. Yeah, there's another series, Life After People. It's kind of the same thing, and it shows you how some cities will, let's say, turn back into jungle or forest, and some will be covered, etc. So that's what you're saying.
Yeah, I had a discussion about that TV show just earlier this week. Yeah, about how if you take away the people, what's going to happen? First thing, you'll start having trees grow in the middle of the streets, and then it just takes over from there.
Well, as a geologist in the know, when you watch those programs, are they accurate, or are you like slapping yourself in the head saying, "Oh, geez, this is totally made up stuff"?
Well, television shows run the whole gamut from big smiles to slapping one's head in disbelief. So, some of them are great, some of them are not, but many are great. Many are great.
I guess getting back to radiometric dating. So what's involved in radiometric dating, and what are some of the compounds used, and how do they work?
Well, what fundamental behind here is the recognition of radioactivity. And this radioactivity was not understood until about 100 years ago, 125 years ago or so. And so we now understand that certain things, certain nuclei are unstable, and they will decay to something else. And that just happens once in a while. And some of these things are more unstable than others. Carbon-14 is perhaps the most well-known example. It is relatively unstable, but it has a half-life of 5,730 years, which means that if you start off with a pound of carbon-14, in that many years you'll have a half a pound, and in that many years more you'll have a quarter of a pound. So it goes by half every time. Now, 5,000 years isn't really very long to be able to look at geology, which we understand now goes back billions of years. But there are other isotopes which decay on a different time scale. The two that are most commonly used in geology are uranium. Uranium actually has two isotopes, but the most important one is uranium-238. It has a half-life of about 4.5 billion years. So the age of the Earth is about 4.5 billion years. So we have about half as much uranium-238 as we did when the Earth started. Now, that seems like a very long time. Of course it is, but we have minerals that have enough uranium in them, for example, that in just a few million years, and by the way, that's a phrase that geologists are much more comfortable with than most people around the world. We say just a few million years all the time and don't think anything about it. In just a few million years, enough lead, the daughter product of uranium, or one of the daughter products of uranium, will build up into a mineral, and we can measure that daughter product that came from the uranium, and then we can figure out how old it is. The other most important isotope in dating is potassium. Potassium-40 is one of the isotopes of potassium, and it has a half-life of about 1.25 billion years, which again seems like a long time, but it's just about perfect for dating rocks, because the rocks we have available to us, whether from the moon or from this planet or even from meteorites, they don't go much older than 4.5 billion years. And so a half-life with 1 billion years will cover the old ones, but minerals with lots of potassium will also be able to be dating stuff that's quite young. So we can date rocks that are as young as a few thousand years to several billion years, generally with a precision of approximately, always better than 1%, sometimes a lot better. But
where in the half-life?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now, back to the show.
If I'm going to use carbon to date something that's millions and millions of years old, it's no good. Why? Because it had gone through so many half-lives that there's barely any material left.
That's exactly
where
right.
Where is the sweet spot of half-lives, number of half-lives, where you can get a very accurate prediction?
The sweet spot would be 1 half-life. That's really the best place. You'd always, if you've got a rock that's 1 million years old, the best thing to do would be date it with 1 million-year half-life. If you've got a rock that's 1 billion years old, the best would be 1 billion-year half-life. But the sweet spot isn't really a spot. It's a wide range, and it depends on not only the half-life and the age of the rock, but the mineral you're using. Are you using a mineral that's got lots and lots of potassium in it? That's better. If you have a mineral that's got almost no potassium in it, that's bad. Also, how big is your sample? Can you shovel the material into the mass spectrometer, or do you have to work with some precious little, grain of sand that came back from the moon? So the sweet spot is a combination of these things. How old's the rock? What's the half-life of the system you're interested in using? How big is your sample? And how much parent can be found in that mineral? Well, by jiggering those things around, you can find many opportunities to put a number to the age of many rocks.
Well, it seems like there's a big gap. I guess carbon-14 is 5,700 years half-life. Then the next one, potassium-40, you said is 250 million.
Now,
so is there
potassium-40 is 1 billion years, but that is a big gap in half-lives. But the fact that potassium-40 has a half-life of 1.25 billion years doesn't mean we have to wait 1.25 billion years to use it. In fact, some rocks have been dated using potassium dating that are, a few tens of thousands of years old. And that again comes because if you have a big sample and a lot of potassium in your sample, you overcome the fact that it's decaying kind of slowly.
Right, but I mean, if I'm going to date a rock that's 5 million years old, and the closest thing I have is either 5,000 year half-life or 1 billion year half-life, I would think that for certain things of certain ages, there's going to be a lot of inaccuracy. Is there a compound or a mineral or some kind of element that has 1 million year half-life?
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
There are a bunch of different ones, but the reason we like the potassium so much is because there are some minerals that are 10% potassium. So that's the key thing to remember here, is that we don't really care about how fast it's decaying. We just want to know, has it decayed enough daughter product? And in the case of potassium, the daughter product is the element argon. Potassium argon decays to argon. Potassium-40 decays to argon-40. And so we don't really care how fast it got there. We just want to know, in this thing we're going to measure, is there enough argon to measure? Now, if you wait a very long time, there will be some there, but you can get it in a shorter amount of time if you have a lot of it there. Think of a group of people in a small room, and you ask them all to flip a coin, and let's say we got 25 people. Let's say we have 24 people. You flip a coin, and you should get 12 heads, right? But if you did the same experiment at a football stadium that was full of 100,000 people, you flip a coin, and you'd get 50,000 heads. It's not because their quarters are more likely to come up with heads. It's just that you had more of them to flip. And that's the same process we use to leverage dating, is we pick minerals that are full of uranium or full of potassium or whatever other system we want. If you try and date the mineral quartz, for example, you can't date it with any system you want because it doesn't have any of the good stuff in it. But a mineral like potassium feldspar, a mineral has lots of potassium in it. A mineral like zircon has a lot of uranium in it. And so it's a combination of the age, the half-life, the size of the material, and your ability to measure.
So what are some of the factors that would make a measurement inaccurate that you've observed?
Well, any measurement, you can screw it up somehow. That's like saying, how tall is somebody? You get out the ruler and you measure it. And so you can type in the wrong number. You can do all sorts of things. The inaccuracy is not the biggest problem. The real issue is, how well do you know an answer? If you say this rock is 100 million years old, that may be the case, but how certain of you are? Is it 100 plus or minus 1? Or is it 100 plus or minus 10? Or is it 100 plus or minus 0.001? And that's the big challenge these days. And it keeps getting better, because technology keeps getting better. Our ability to have quiet electronics, and that's really what it's all about. Machines that can tell the difference between 0 and almost 0. And how far down can you push that almost 0 to be? And, it used to be 50 years ago, say, that rocks would be dated, and if you could get 100 plus or minus 5 million years, you were considered an okay lab. That was a bit of progress to help us out. But nowadays, if somebody were to go to a meeting of geologists and report that they dated this rock to 100 plus or minus 5, somebody's going to ask, why did what went wrong? Was there a thunderstorm in your lab that day? Because generally now, because of the quality of the instruments, things are just much better, and every measurement is quieter. And so when you see that signal coming out of the machine, it's a nice steady signal. In years past, it was a more wavy signal, and then you just had to figure out, well, where in that wave are you going to pick the number?
Oh, for the measurements you make, if you're measuring something that's, several million years old, what's the ballpark range of age? Like, how specific can you get?
Well, it's always best to describe it in terms of a percentage. If you had a rock that was 100 million years old, we can date it. It's always going to be about 0.5% or less. So, or maybe, sometimes now we can do as well as 0.1% in very good instances. So 1% of 100 is 1. So 0.1% of 100 would be 1/10 of a million years, or 100,000 years. So we can now date a rock that's 100 million years and expect to have the uncertainty range be within a few 100,000 years, or sometimes even better than that. And it's really important that we continue to do better and better, because if you want to ask a question about, how fast did global warming take place in the Cretaceous? Well, you have to be able to distinguish between an event that occurred just a few thousand years apart. We can do that for rocks that are, 1,000 years old. We can tell the difference between 1,000 and 1,050. But you can't, that's a wonderful sort of precision. But that precision is going to blow up when you go back million. And so what manufacturers of these machines and geologists pushing their machines are continually trying to do is be able to say that we can add that level of precision to the long ago, because glaciers didn't move over millions of years. They moved over thousands of years or hundreds of years. And the kinds of things we're interested in the young rocks, we're interested in the old rocks too. It's just that it's harder and harder to figure that out as you go deeper and deeper into time. But in general, it's about 0.5% of the total age, or better nowadays.
Yeah. How do you know the accuracy is what it is?
Well, I'm talking about precision. Accuracy is a whole nother problem. Accuracy means we got the right answer. And the way that we have to do that is, accuracy it's a trickier business, but sometimes we can actually date rocks. We know when they happened, like the Vesuvius eruption I mentioned earlier. People have actually been able to use geochemical techniques to date that event. Now they got, that happened in the year 69 AD. So if you were to date that today, you'd get an age of, 1960 years or something like that. Well, they actually dated it using these techniques, and they got an age of something like 2,000 years plus or minus 200 years. And so that's an accurate value. We know that. So when we are dealing with rocks that we don't know how old they are, we have to just rely on calibrations. We know that certain things are true. We measure that in our laboratory. And if we can get some things we know are right, then we can go ahead and do things that we don't know. But the question of accuracy is a real philosophical conundrum. I mean, if we knew the answer, we wouldn't have to go to all this trouble. But
but how do you infer that something is 4.3 billion years old and it's not 2 or 1? Or
okay.
How do you know the accuracy with those deep time estimates?
Well, because we have a good feeling of what the rate of decay is. And that has been established by a variety of ways. Sometimes some rates of decay, like the decay of rubidium-87 decaying to strontium-87, that was measured directly. And what was done is you take a scientist, got a bottle, and filled it up with a whole bunch of rubidium-87. That's a radioactive element. I mean, a whole bunch. I mean, like a pound. It's just an overwhelming amount of this stuff. They purified it, and then they measured it, and they said, okay, we've got this much rubidium-87 in this bottle, and we've measured it, and we can only find just teeny traces, or maybe no traces at all, of the daughter product, which is strontium-87. Well, then they put that jar in a cabinet, and they came back 30 years later. They had to wait a long time. From our perspective, 30 years is a long time. It's not much in terms of rubidium-87 decay. But that was enough time, because the bottle had so much parent in it. That was enough time to come back and find enough of the daughter product to measure. They measure that daughter product. They say, okay, we started out with this much. Now we've got some daughter product. We know exactly what the time was, because they just count the days. And with that, they were able to calculate what is the half-life of that system. And so that system has been measured directly. Other systems are measured in comparison to other systems in situations when we know that the rocks should have the same age. And that's the best example of that would be volcanic rocks, because volcanic rocks have a simple history that's not concerned with temperature, because a volcanic rock goes from very hot to very cold very fast. And so it shouldn't matter what system you used in terms of thermochronology, you'll get the same answer. And even better than being a volcanic rock would be a volcanic rock that's never been rained on. And you might think, well, where are we going to find something like that? Well, all you got to do is go to the moon and pick up some of these volcanic rocks. And they have been brought back to Earth here, and places like NASA have studied them. And a volcanic rock that's never been rained on is the simplest system we can imagine, and one in which we have every expectation that the ages should be the same. So if we date that rock by one system that we know the half-life of, and then we measure the parents and daughters of another system that we're unsure of the half-life, we can then determine the half-life by saying, what is the half-life it would take in system number 2 to get the age that we got out of system number 1? So by comparing the half-lives of various systems, by measuring some of them directly, we have a pretty good sense of how fast these things decay. And then it's just a matter of how well you can measure something. When you get that signal, it's an electric signal that comes off these machines. Is that signal nice and quiet? And you can say, aha, that's a signal of 2. And then there's another signal of 3. And so you've got a ratio of 2 to 3. However, if that signal's coming off real jumpy, and, you've seen, things that jump around, and you go, is that a 2? Is that a 2.4? If that's the case, then the value you get is going to have some uncertainty in it.
I don't know if it's a BS argument or not, but is the half-life invariant over long periods of time?
It's an essential question what you're asking here. Because if it changes over time, then we have a real problem. I mean, imagine I've got a bucket, and you watch, and I'm filling it with water, and you didn't see me start filling the bucket, but you walk around the corner and you can see me fill in the bucket. And you can measure, well, it looks like you're adding about 1 liter per hour into that bucket. And so there's 6 liters in the bucket. Okay, you've been doing it for 6 hours. But that assumes that the rate at which I'm putting water into the bucket now is the same as it's always been. If it isn't, then your calculation's going to be wrong. So it's an essential question. But by these sorts of comparisons that I'm talking about, by looking at rocks from the moon, where we have very essential understanding about what the rock's expected ages are, by measuring things directly, by comparing gobs of different things in many, many examples, there is no reason to doubt that the half-lives have been constant over time. We also don't have any evidence that half-lives depend on pressure or on temperature, that as you push a rock down deeper, that doesn't affect how fast the uranium is going to decay. But it's not at all a trivial concern what you're bringing up. It's essential, and we evaluate that problem all the time. But right now, no evidence indicates that this is a serious problem.
Any other potential sources of inaccuracy? Like if you have a rock, it wasn't always, let's say, a rock. Perhaps there was a migration of some of the materials that comprise the rock, which would change over time, when it was actually finally or truly formed?
Yeah, well, as I mentioned, we'd prefer to have rocks that were never rained on because, and I should point out that when we're talking about dating rocks, we really don't date rocks. We date individual minerals because individual minerals have specific characteristics that an entire rock doesn't really have. If you have a rock with a bunch of potassium feldspar in it, as opposed to a rock with a bunch of olivine in it, you're going to get different things. So we take just a mineral, but the problem then is to determine whether this mineral is in its pristine shape. And often that's possible to look at it and say, well, the one thing you've got to worry about, has water come through this system very much? A lot of water can be a problem. And I don't mean just, a rain shower, but many years of material water going through a system might change the chemical composition of the mineral. And particularly in the case of potassium, if you were to remove some potassium from some minerals, and that can happen, you would then misunderstand what the proper age would be. But we have ways of trying to test against that. We look at the minerals microscopically to look for visible evidence of alteration by water or other fluids. We can have ways of testing their chemistry of the minerals as it goes from the outside of the mineral to the inside of the mineral. We have expectations of what those variations ought to look like. And if we see evidence for alteration of the mineral, then that becomes a candidate to put to the side. That's not a good choice for this. We prefer to look for these rocks that have no good evidence of large scale changes. Now, in the matter of the rocks just being heated up, that's not a problem, and that will simply produce minerals that cool slowly. And as I said, thermochronology is the ability to pick some minerals that would tell you about a high temperature and some minerals that would tell you about a lower temperature. But if that then, after you got to that second temperature, if the rock was then infiltrated by a bunch of water, that could be a problem. But as I said, we have ways of examining the rocks to give us confidence that didn't happen.
Yeah, I guess if you're trying to look at sands or silts or things that are in a flow state instead of just rocks, it would be, I don't know, can you get any accurate measurements? Like if you're in a riverbed, an ancient riverbed, how do you know what to sample? It seems like there's a lot of, there's a lot of expertise. You need to know maybe the context of where you're sampling, what's around it, what it might have gone throughout the years, et cetera.
Well, that's true. It does require a good eye to know what constitutes a strong sample and a weak sample. It also depends on, we also gravitate towards certain minerals that are more robust than others. Some minerals are really bad choices for these concerns that you're raising, and others, like the mineral zircon, is very hard to disturb because it's just so chemically and physically strong. So all of that goes into making the right choices of which minerals to take to your laboratory.
Okay. Any other factors that you've seen that can confound measurements? Or again, it is pretty reliable that 0.5% or maybe 1% is the typical accuracy. So, how robust is dating, the science of dating? Is it pretty robust, or where is it at for right now?
No, it's quite robust. And like I said, in years past, 1% was considered good. Nowadays, 0.5% is considered good, and as we move through this, 0.5% will be considered, sort of on the bad end. And it's just because of the improving technologies. We live in a world in which, every little electronic device is becoming better and better. But 50 years ago, people didn't carry around little computers in their pockets that also made phone calls. And that, the kind of electronic improvements that have gone into your cell phone have gone into all of the machines that we use in our laboratory. So the ability to make these measurements is just getting better and better all the time.
Yeah, last question. So if I have a rock with certain radioactive material and it releases that material and then affects other elements in the rock, can you do a secondary corroboration of a date by looking at other minerals in the rock? Let's say I have uranium, 235, and what it emits changes some other mineral in the rock from A to B. Can I also look at that accumulation or accretion of the other material that was caused by the initial radiation to let me know a date?
Well, there is a kind of technique that's a little bit with what you're talking about. It occurs that there's a special kind of radioactivity that's called radioactive fission. And in that case, a uranium-238 atom will break up into two pieces that are about the same size. A lot of this other radioactivity will knock off little bitty pieces. Fission decay will take a piece of uranium and which has a mass of 238. It will break it up into two things that have a mass of about 125, 120, something like that. And those two relatively big pieces, because of the energy associated with this radioactive decay, they shoot off in opposite directions inside the crystal. That actually creates a damaged track inside the crystal. The crystal becomes damaged, and this zone of deformation inside the crystal is called a fission track. And we can, by preparing these minerals in certain ways, putting a little acid on them to make these tracks show up better, these tracks then become a damage indication of radioactive decay. And so it is kind of what you're saying. It's not in different minerals, it's in the same mineral, but this produces a physical damage in some minerals. And then you can count up, and this requires you just looking down the microscope. You count up how many, that's a fission track, that's a fission track, and you count them up, and that how often they occur. And so that's another way of dating something, not by measuring isotopes in a mass spectrometer, by actually looking down a microscope and saying, oh, there's one of those things, there's one of those things. So sometimes, radiation will cause damage into crystals, and that damage is sometimes useful to turn into chronology.
Well, very good. Peter, what's the best way for people to find out more about your work? Where can they go?
My work, I suppose, Google Scholar, would be a good place to type my name in and see what sort of research I've been involved with. Generally, isotopic dating, is found in lots of popular sciences. Whenever you're talking about geology, there'll be some reference to the age of things, and so the applications are in all geologic concerns. But my specific work, I guess I would suggest going to Google Scholar.
Very good. Well, thank you for coming on the podcast. It was really interesting, and I appreciate it.
Oh, my pleasure.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.